I wanted to do another example of factoring polynomials via synthetic division. As we did in class this week, just wanted to do another example for you guys because we did it pretty quickly, and just wanted to make sure you had a resource to come back to if ever you were feeling stuck. And just to sort of remind you, it's predicated on two polynomial theorems that we also discussed in class time: the remainder theorem and the factor theorem. And really the key behind this theorem is that if I can find a zero value for a polynomial function, I know that that must pertain to a particular factor within the polynomial. And if a polynomial has a zero, that means I can use synthetic division to divide it up. And that's exactly what we're doing when we use synthetic division to factor polynomials. We're using basically the conclusion of the factor theorem to help us fully factor that polynomial function, as we did with one of the examples. And in the next few lecture module videos, we're going to discuss other theorems and look at those more closely. So let me pull back up the lecture packet and remind you that one of these pages we did during class, so this week. So I'm just going to jump to the next page and start fresh. And so just to sort of reiterate, how do we factor a polynomial using synthetic division? Basically, step one, one of the ways you could do it is by using a guess and check method. If we're looking at a polynomial function, we could say, well, maybe 1 is a 0, maybe 2 is a 0, maybe 3 is a 0, and so on, kind of randomly guess zeros until we find one that works. And how we could test it is by using synthetic division, right? Because when I do synthetic division, that's the same as evaluating the polynomial when I get the remainder. And when I get a remainder of 0, I know it is a 0, and therefore I have found a factor. But that's really tedious because basically I'm guessing without any other information. And the next theorem I wanted to discuss very shortly is what's called the rational zeros theorem. It's a theorem which allows us to basically make more educated guesses about what are the possibilities for the zeros. But anyways, what's a lot easier is, instead of guessing at the zeros, we can use a graphing calculator or any calculator which will create a table of values for you to determine the zeros which are rational, or the ones that are easy to find. So let's say I wanted to start by factoring this polynomial p of x. What I could do is type it into my calculator. So I have 2x to the 5th minus 7x to the 4th minus 31x cubed plus 21x squared minus 36x, and just see what I'm working with. And again, I want to focus on the x-intercepts because the x-intercepts will allow me, the x-intercepts are synonymously the zeros, and those zeros must pertain to the factors. So if I find the zeros, I find the factors, I know exactly what to divide by. And it's kind of hard to see, but it appears as though the graph crosses at -3, 0, and 1, 2, 3, 4, 5, 6. Let me go ahead and make this a little bit bigger so that y'all can see it better. Another tactic which I was discussing with some of you guys during class time is what's called the zoom fit function. I just wanted to mention what that does for a polynomial. If I use zoom fit, what will happen is it'll alter the window to match and show you more of the behavior of the polynomial function. Though sometimes it can be harder to see where those zeros are. Like in this case, if I use zoom fit, it doesn't actually look very good, but I can see the polynomial comes up from the left-hand side. It appears to cross somewhere over here, comes back down, but in this particular case, it was not very helpful. But at the end of the day, if I just take the Y window, and I can kind of see what happened by going into the window command, it looks like it zoomed way out, and maybe just altering it to say from -200 to 200 might help me see it a little bit better. But you can always play around with your viewing window, and it might help you see the behavior of the polynomial a little bit better. In this case, it appears to be, maybe it's -3, 0, and 6, as I said before. But again, how do we know? How can we verify? Well, we could just do synthetic division. That's kind of the whole point of the those polynomial theorems that we were discussing is that I can check for divisibility and factorability synthetically. So let's go ahead and do that. So I want to start with my original polynomial function p of x, and I'll go ahead and put it in synthetic division. And basically my goal is to factor this polynomial. And over here I'm going to keep track of my answer that I'm getting from synthetic division as I go. But again, we're going to list the coefficients of the polynomial within. Also, notice that this polynomial has no constant term, or basically it's does not have just a number at the end. But as I said before, make sure that you insert zeros into each slot which has a missing value, and that is the case for constant value within a polynomial. So if I was to not put that zero there, I'm going to have a bad time. And here again, the question is, what am I dividing by? But that's the whole point of the graph. Is the zeros are what are the zeros give me the roots of my polynomial, and those are what I want to divide by. So for example, 6 is one, or 0 is another. And actually 0 is a little bit more obvious, because notice that there is a common factor of x within this polynomial. And that's another thing that you probably would have noticed before even doing anything else. And usually a recommended strat with polynomials is to factor out any common factors that it would have had. But noting that this polynomial actually intersects at 0, that's not a coincidence, because x all by itself is the one case when you can have a factor of 0. X minus 0 is the same as just x. But anyways, that's why I don't want to start with 0, because if I try to do 0 here, it's not going to work. Actually, it will. You're just not going to do anything, and you'll see what I mean. But let's go ahead and use 6 just for no real reason, because again, that is one of these zeros which appears on my graph. And if I go ahead and start the synthetic division, drop multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. What I end up with is, and actually notice that the 0 at the end was kind of awkward. And when I actually factored out x, I sort of dealt with that 0 to begin with. So I didn't really need that, because the remaining polynomial after factoring out the common factor of x is just 2x to the 4th, negative 7x cubed, minus 31x squared, 12x, and negative 36. So basically, I'm just going to factor that out first. That way I don't need to have that 0 at the end. But it's just going to make my life a little bit easier. But basically, notice I do get a 0 remainder. Cool. And what's left over over here is the quotient, or the remaining factor, 2x cubed plus 5x squared minus x plus 6. And again, as I'm going, basically I took this whole component and I factored that in. And remember, that's the whole point of division, right? If I get a remainder of 0, that means that it was divisible. And if I think about, well, what did I actually divide it by? I divided by x minus 6. And what's left over of the division is 2x cubed plus 5x squared minus x plus 6. And this is, again, what I mean by when I say use synthetic division to factor. Basically, I'm going to determine my zeros from a graph. And using a graph is just a shortcut to find them, so that I don't have to randomly guess from, without having any other information. And then I can keep going, because I can also see, well, it appears as though maybe minus 3 is a 0. The graph, it's kind of hard to tell because it looks like it might be slightly off on the graph, but graphing calculators are not always perfect. So let's just check. Negative 3, and we will know if we get 0. So drop, multiply, add, multiply, add, multiply, add, 0. So indeed, it is divisible by x minus 3. And as I'm going, my polynomial is getting simpler, because now what I did is I took this polynomial, which is right here, and I divided by x plus 3. And when I divided by x plus 3, what I got is 2x squared minus x plus 2 with a 0 remainder. And the thing of it is, well, as we're going, as we continuously use synthetic division, my polynomial is getting simpler and simpler and simpler. And at some point, I'm going to run into a polynomial which, well, maybe I'm stuck, or maybe I've kind of, can return to a more traditional matter of factoring. And now once I get down to a quadratic, that's something where we know, well, what are the zeros? We could always use the quadratic formula if we weren't really sure. And the thing about this particular example is that I only really see 3 zeros, and so far I've already factored those 3 out, by GCF and then by synthetic division. But once I get to here, if you have, and this is kind of what my point is if you ever run out of zeros, what do? Well, we could revert to other tactics like the quadratic formula. And the quadratic formula is, well, I would take negative b plus or minus the square root of b squared minus 4ac, 4 times 2 times 2 is 16, all divided by 2a, which is 2 times 4. Sorry, 2 times 2 is 4. And basically, I could come up with, well, what are the zeros of this polynomial if it has any? And something that we know about quadratics is that it doesn't always have zeros, because sometimes the parabola doesn't cross the x-axis, and in those cases we often run into what we often refer to as imaginary zeros or complex zeros. And that's something we're going to expand upon in 5.6 and talk a lot more about the complex number systems, and that's all coming up very shortly. But for now, we're focusing on real zeros, because that's what we're working on just for the time being. But we will come back into complex zeros soon. But basically, from here, often what we say is that this component is a prime polynomial because it can't be factored any further. And if you try to factor it using a magic X method or whatever other techniques you covered in high school, you would get stuck. And that's kind of my point is, well, how do I know when to stop? And can I progress any further? But in this case, we'll leave it at this, because this polynomial, we'd run into a square root of a negative, which would become imaginary. And technically, you can factor polynomials that way as well, but we'll get to that later. But if I'm dealing only with real numbers, we'd say, well, this is our final answer, and we've factored it using a bunch of linear and quadratic factors to finish this sort of problem.